Okay, ready? Hope you're ready to resume this session. Quite interesting this morning with nice presentations, nice information, interesting information about the problems that we are discussing today, and possibly with proposals that I hope will emerge during this morning, this afternoon, tomorrow. I think that we need to be concrete and proposals, policy proposals about how to alleviate the energy poverty problem are really relevant. But in the meanwhile, let's give the floor to Professor Chakraborty from Tufts University. I'm very pleased to have him here. You need to talk from the podium. Thank you. Thank you very much.
Thank you, Carlo. Thank you, FEEM, for inviting me. It's a pleasure to be here. Never been in this beautiful city, and I'm hoping that I'll run into Giorgio Armani in the street somewhere outside. But I guess I'm going to talk to you about the quality of electricity. And this is a joint work with two colleagues, Martino Pelli, who's a new assistant professor at the University of Sherbrooke in Canada, and Beza Marchand, who's at the University of Alberta. So basically, you've actually heard a lot of the important issues in energy poverty and energy access, especially with respect to electricity. Many of you might remember this big power outage that happened, I guess, about 2 years ago in India, where 10% of the world's population lost electricity. And so this is indeed a huge problem, especially in India, surprisingly, relative to other developing countries. And as Shonali mentioned, and also Jacopo mentioned, the numbers, I mean, they're actually phenomenal. 300 million. I mean, you can see the numbers are getting better in terms of more people getting access, and I'll show you some data on the quality of electricity supply, which is the sort of major sort of contribution of the work that we were doing. But still, the numbers are huge, and they matter a lot in terms of allowing for equal economic opportunities to people. If you look at the per capita consumption in India, it's about 560 kilowatt hour relative to about 2,700 for the world. So yeah, the numbers don't look good. You can see the graph here. India is lower than sub-Saharan Africa in terms of per capita electricity consumption. And China is much better. China has done a much better job of allowing access to electricity for its citizens. You can see here, the India and United States, again, a huge gap. There's some, there's increasing interest in, I guess, within economics, development economics, energy economics, in studying the outcomes from electricity. There are not that many papers that, as Jacopo mentioned earlier, employ sort of rigorous microeconomic techniques to isolate the impact of access to electricity on different outcomes, household incomes, in terms of wages, the value of your assets, agricultural assets, non-agricultural assets, etc. When we started this work about 2 years ago, there were basically a handful of papers, and some of them Jacopo already has mentioned. Dinkelman in South Africa, very nice work on the effect of electrification on employment, and Lipscomb et al. On economic development in Brazil. There's now a new paper out by Martin Ravalian and various other people at the World Bank, again, looking at India, and complements our study with a different approach. and the answers, the results are basically similar in magnitude for a lot of these studies in terms of the outcomes of electricity provision. There are also a bunch of other very useful studies, but they are more descriptive in nature, and we list a few of them here. Especially Modi's paper is actually was very helpful for us. So what we are actually, in this project, which is essentially finished, but I'll tell you a little bit at the end on the extensions we are pursuing in answering some more questions on the impacts from electricity provision. What we are actually focused here is two things. One is, what does it do at the household level when your household gets connected to the electric grid? And the second thing is, how does it, and I think Shonali mentioned this, how does more reliable electricity access, again, what does that do to you in terms of your economic outcomes? And as pointed out by Michael Greenstone recently in a survey paper, I mean, this is, the quality and quantity of power supply is hugely important. And what we do here in terms of the data is basically we use this Indian Human Development Survey. It's a survey run by someone at the University of Maryland, but they have done waves in 1994 and 2005. In fact, we are waiting for the new wave that's going to come out anytime now. And we are actually hoping to go back, and I'll give you a little idea of some of the data that is insufficient or inadequate for our purposes that we hope to be use the third wave to increase the sort of reliability of the estimates we make. But we have 10,000 rural households. They are nationally representative sample, and the survey goes back to the same households and interviews them in two different periods. The only thing is, because of confidentiality, we do not have the location of the villages where the data was collected. So we do not have, we know which district, we know the characteristics of the district, but we do not have location information. And that inhibits our work to some extent. I'll tell you a little bit about that. We have data on all household wages and all non-agricultural income. So we don't have agricultural income. And the reason is, in 1994, when they asked questions, they did not allow for negative responses to agricultural incomes. So we do have data for 2005 agricultural incomes, and when the new survey comes out in 14, then we could add to our estimates in terms of the effect of electricity provision on agricultural income. So that's definitely going to be a big improvement on the stuff that I'm going to present to you. Just to give you a sort of takeaway here in terms of the main sort of message from this analysis, essentially we find that it's hard to isolate the difference, hard to isolate the effect of quality from the effect of grid access. But if you just look at grid access, you get about a 9% increase in household income in between those two periods, 94, 2005. But if you add the impact of increased quality of supply, you get about a 30%. So we are talking about quality being as or more important compared to grid access, if not, as important, if not more. So again, given that this is a sort of microeconomic study, we needed to worry about the endogeneity of our regression. I mean, if you go and collect data from households and then run a regression that has returns on the y-axis and electricity quality or access on the x-axis, you have this problem of endogeneity, meaning that governments, for example, could be targeting electricity to high growth areas. So then you get your growth estimates and they are, biased. You get higher growth estimates and you say, well, this is the contribution of electricity. It might be something else going on. The fact that policymakers target these investments in different areas. So we take a lot of effort in trying to make sure that we are capturing
or we are taking out some endogeneity here. And what the data actually, which is unique in this paper, and I'm getting a lot of requests from other people to share this, this data, is actually the density of transmission cables. So we have by district, we essentially have a GIS map of India, and I'll show you in a second, with all the transmission cables lined up in each of these districts. And the reason we say we think that that might be less endogenous is because transmission cables essentially connect, power generation to cities. I mean, you don't really think about, and our analysis is based on household data and villages. So you're not, you have a coal-fired, power plant, and then you say, okay, I'm going to, build transmission cables that take, electricity from this power plant to this area that is, a whole bunch of, let's say, cities or big cities. However, on the way, because you are taking it from location A to B, you might be traversing rural areas. And that's where we are actually doing our analysis. And I'll tell you a little bit more about some of the robustness checks we do to make sure that we are not capturing, growth that is coming from other, the location of the village near a big city or urban area and so on. So, so this is a schematic of the power grid, and you can see here that it's a very basically this simple idea. You generate electricity, you ramp up the voltage because that's when electricity losses through transmission are low, moving across these transmission lines, and then again you ramp down the voltage to allow that electricity to move through smaller, less thick distribution systems, and then finally you're really at the low voltage to be able to connect to households, villages and households. So here is our sort of story. So you have a power plant and you have city A and city B, and you can see that transmission lines would be located essentially along a straight line. If you look at the map of transmission lines, I'll show you in a second, they basically they are very expensive. You have to build poles, often in remote areas, but you have to maybe overcome barriers, topographical barriers such as mountains or rivers or forests. And you can see sometimes that they bypass these barriers, but essentially they're going, from as the crow flies from A to B. So here are our villages, and you can see some villages lie along a transmission line, and others might be away from transmission lines. So our basic sort of working hypothesis is that the cluster of villages in the middle it's less likely that they will be connected to the grid, and it's less likely that they'll have reliable electricity supply. Because if you are, along this transmission system here on the left, for example, I can use our marker here. So these guys here, there's less likelihood of power outages because you have a bunch of transmission cables. If one of your distribution lines goes out, other lines might step in and provide you electricity. So that's basically our idea here. And you can see, so this is a good example we picked up, I think, from Google Maps. So you can see here, there's a power plant, thermal power plant, or location here, there's a thermal power plant here, and then these are transmission lines, and you can see basically they're going straight line. And then this is Hyderabad here, a very big metropolitan city in India. Warangal, not so big, but pretty big. Every like I always tell people, the top 20 cities in India would be very big compared to, say, standard European cities in terms of population. Etc. But so here is the transmission line that's being connected along a triangle. There is, I think, some green areas here and so forth. So if you look at the map of transmission lines in the whole country, you pretty much see the same patterns. So here we have transmission line density by district, and you can see that there are some white areas, which means basically there are no lines there, which makes our study nice because we can use that variation. So the other thing that we worry about is, well, how was quality determined in the survey? And here again, there is a little bit of a problem because between 94 and 2005, you can see the questions about quality were different. For example, in 94, the question was, how many weekly outages do you get? And you have, if you have no power, obviously your quality, so we said if it's no power, the quality is 0. If you have 1 to 2 or more than 2, it's 0.5 and 1. So it's an approximation. We do some robustness checks after. But then in 2005, the questions were much more narrower. And here the question, the question was, well, how many hours of average electricity supply do you get every day? And you can see the cutoff was 18 hours. And here again, we try to match these. So you develop an indicator to make sure that we are trying to catch the same thing, but then we do a whole bunch of sensitivity analysis, and that our results basically hold. So instead of 18, we do 16 and 17 and 19 and 20 and so forth. So here is our grid connection and quality between the two periods, and you can see between 94 and 2005, for many of these states, there has been increased access. The number at the bottom tells you 53 to 69%, and then 39 to 71% change in the quality of electricity supply. So if I look at the regression here, basically, it's a standard regression where on the left we have the log of income per adult equivalent, and on the right we have a bunch of variables, including a constant term alpha. Then we have household fixed effects, we have time fixed effects, things may be changing over time. We have district time interacted with time fixed effects. We have the instrument, and which is at the level of the household. I'll explain that in a second. Then you have a whole bunch of other variables and an error term. So that's our, so we try to take the time difference between the 2 years, and you get this lower equation, which I will not try to explain. One of the big issues here when we gave seminars earlier with this work, people said, well, your transmission cable density is at the level of the district. So your instrument is at the district level, which is a more aggregated level than the households that you're studying. So what we found was some literature that in labor economics that tries to adjust this, a more aggregate level of the instrument to the level of the household. And basically we multiply the deviation in the transmission cable density. So we normalize the cable density, divide by the area of the district, take the deviation from the average cable density in the country, and then we multiply it by the initial level of quality of power supply at the household level. So that way we get an instrument that is at the household level. And so here is our system of equations. I'm going to go through this fast. Essentially, the first stage is pretty reasonable. You can see on the left, the 5 of those columns is grid connection, the effect of grid connection, and the right is the quality of supply. And you can see that you pretty much get consistent level of significance, and the F stats, etc., are pretty decent. And then you get some other, important sort of significant variables, such as the size of the household and the children. If the children, more children, potentially there's less lower economic outcome in some sense, because maybe people are spending more time taking care of their kids. And then you can see the effect of power supply on household income. Here again, the important thing to see, you can look at the OLS and the instrument variable regressions, but let me see. Yeah, I mean, the last, the column, for example, gives you the IV regressions here, and you can see the effect of quality of power supply is pretty significant. It's about 0.9. And the OLS estimates are pretty low. And so the OLS estimates, of course, and this has been, I think, also consistent in the literature by Dinkelman and so on. OLS estimates are lower than IV estimates, and one explanation could be that when it comes down to distribution lines, then the state governments are in charge of taking the power from transmission lines, moving into distribution through the distribution system, and targeting villages and households, and that might be politically motivated. They might, for example, be targeting lower growth areas, for example, or poorer areas. So you get lower impacts in the OLS regression relative to the IV regression.
Just a question. Do you have the log of the change of quality or the change of quality?
This is the change in the quality.
Not the log of the
No,
change
not
of quality.
the log is the income.
Only for the
Yes,
income.
yes. Where did I lose my? Okay, so here we were. And okay, so the robustness checks, again, you know, the trick here is to make sure that you're not getting something that's sort of out of whack with or is sensitive to certain assumptions. So do a whole bunch of things, including you know, cable density. We divide by population, not area of district. And here the point is, well, you know, districts are big in India. It's a big country, and you know, some parts of the district might be completely unpopulated. So we are capturing, by dividing by the area, we are you know, ignoring the heterogeneity within the district. And we get similar results. You can see our paper, which is on my website, for the details. We also eliminate this big concern with high growth states and investment in high growth areas. And you can see we took out coastal states like Gujarat, which are much more developed than the rest of the country. Similar results. We eliminated same party in political power in the federal government and in the state government. No change in results. Here again, the idea is that the transmission lines are actually built by federal government and the distribution lines are built by the state. So to the extent that there is coalition between the two to target certain areas, et cetera, we could capture by eliminating, you know, the states where the federal government and the state government had the same political party or the same coalition in power. Then we eliminated high growth states. We also, again, the other concern, as I mentioned earlier, was, well, what if the village, as I showed you in that you know, line diagram, is close to an urban growth area? Sorry. So here we look at districts with 10 largest cities in the country and basically took out those districts and did an analysis of the rest of the districts. Not only did we do that, we took out the 10 largest cities and then took out all their neighboring districts, just to make sure that we are not trying to capture some of these urban you know, growth effects. We also, like I said earlier, altered the definition of quality. And I guess I have 2 or 3 minutes, so I'll wrap up. 2 minutes, thank you. So the conclusion is that, you know, the quality of electricity supply, less outages and more hours of supply may be as important as connection to the grid. And of course, much more research needs to be done to understand the channels through which electrification works. And here, we're doing some work with Rémi Basilier, who's at the University of Paris and Orléans in France. And we are basically targeting the labor market outcomes. You know, what happens to you know, the demand and supply of electricity when you get electrification and access to better electricity. So here we are trying, I mean, this is very much work in progress. We are trying to isolate the labor demand and supply effect. And the idea is that at the more aggregate level, you may have districts where higher degree of electrification creates demand for jobs, you know, industries, labor, et cetera. And then on the other hand, at the household level, at the village level, the electrification changes the supply decisions of the household. And again, I'm not going to go through this. It's work in progress. In some time, you'll probably see some of these results. Another thing that we are doing with energy access, just to finish up here, is actually a paper on firewood markets. And this is different from electricity, but we have, again, some data from the same survey in India on how much time do men and women spend walking to the forest and collecting firewood. And here, we are trying to look at the effect of reduced forest cover on domestic economic activities. And we actually find some really interesting results. So basically, 88% of our household is collecting firewood and buying and selling firewood. And we find that a lot of the firewood basically goes to the closest urban center. And you can actually see a price gradient away from the city and difference in labor allocation decisions, depending on if you're a buyer or seller of firewood. If you're a seller of firewood, you're farther away, you get less price. So you do other things like wage labor. But if you're a buyer of firewood farther away, you actually are better off spending more time collecting firewood. So this is kind of interesting, and this also is obviously another dimension of energy access and poverty that we are talking about. Thank you very much.
Thank you. Thank you, Ujjayan, for presenting almost 3 papers in 25 minutes. I think that beyond the econometrics that may not be familiar to all of you, what Ujjayan tried to emphasize is the importance or the economic implication of energy poverty. In the previous presentations, we heard about the relevance of the problem and how energy poverty may affect health and have social and other implications. But it's also important to quantify the economic benefits of reducing energy poverty. And here we had an example of how, in a specific situation, the alleviation of energy poverty, the solution in particular of some of the problems related to energy poverty, can provide concrete economic benefits and enhance economic development. On the same line, we're going to hear this second paper presented by Stephen O'Connell from City University of New York, again on the effect of electricity shortages on productivity.
Can you give me a 5-minute warning?
Yep.
Thanks. Hi, everyone. Thanks to the organizers of the workshop. I'm really glad to be here, and my co-authors are also grateful that we can add to the discussion on energy access with something, some recent research from the perspective of the firm. So also following the theme of micro-level studies on India, this is our paper, How Do Electricity Shortages Affect Productivity? Also, I'll talk about growth and output and things like that. It's still a work in progress. It's not quite final, so I'll be happy to get any comments that you have. So for motivation for the particular topic, a lot of people are familiar with these figures, but taking from the World Bank Enterprise Surveys, when they go around and ask managers and business owners, what are the main constraints to your operations and growth? In many countries, and these are statistics from India, the #1 constraint is electricity in some form, some aspect of it. And fully 1/3 of managers in India, and I think this is from 2005, are claiming this as the #1 constraint to their growth and operations. So this warrants, for anyone, policymakers or think tanks, academics as well, some investigation into this. And what is it about it, and what can we do? Our question is a very specific one. What are the short-run effects of electricity shortages on firm costs, output, and productivity in the context of India? And we have two potential priors. One, that electricity is, of course, essential, and shortages will result in large losses. There are many papers on this. I mentioned a couple. The alternative is that there are large potential losses, but firms insure or substitute their processes or the things that they do in terms of production to minimize the losses from shortages. Okay? Either in terms of self-generation, which we know is a common thing, especially in India, and I'll provide more information on that in a bit, or substituting different aspects of production or changing actual processes. From an empirical perspective, identifying the effect of shortages is somewhat difficult because of the endogeneity problem. You can have, at the same time, confounding factors such as good economic conditions or general growth, which would increase productivity, and also at the same time usually increase shortages through different sectors demanding more. Or things like poor institutions or low growth, decreasing productivity while at the same time increasing shortages. So identifying these effects are difficult. From a data perspective, as was mentioned by one of the earlier speakers, we don't really have a lot of good data on, at least for this work, on blackouts or shortages, especially historically, or going back, we go back almost 18, 20 years. And from a micro perspective, the manufacturing surveys very rarely capture information on electricity usage and also own generation. In this paper, we get to exploit the case in India where we overcome these typical data limitations. So What I'll present, what we do, it will seem a bit disparate, I think, in the presentation, but in the paper it's integrated a bit more. But we first do a case study of the textile sector in Maharashtra, and we use data taken from an increasingly popular paper on management by Bloom et al. And they collected over a period of a couple years very high frequency information on production in 22 textile plants, pretty large plants over 3 years. And also we couple this with data on known or planned power holidays. So for example, certain plants would be told at some point that they would not receive electricity either for 1 day of the week or for a period during 1 day of the week. And these are foreseen and known. Then there will be a nationwide empirical analysis using a typical manufacturing survey, India's annual survey of industries. It's sort of the workhorse micro-level industry survey for India. The ASI gives us plant-level data back from 1992 through to 2010. And we couple that with archival data on shortages in the power industry, which were actually, records were kept quite well, although we had to dig them up from the archives in Delhi to look at the effects of shortages at the plant level. And we use an instrument to get around the endogeneity problem. This instrument for shortage is hydrogeneration, which is, we're going to claim, coming from really exogenous factors that are not related to the things discussed in the previous slide causing the endogeneity problem. Okay, so a preview of the results, what we find. Electricity shortages at the levels that they're experienced in the last 20 years in India do cause large revenue losses of about 5 to 10%. But the productivity losses are small. That's because the actual amount of electricity input to production is quite small itself. So if you switch from grid power to self-generated power, that doesn't cause a huge overall increase in costs. And productivity losses are smaller than revenue losses because inputs can be storable. The majority of inputs can be saved for a later date to be used for production. Okay? Useful for this session, I think, are some of the things that we did on heterogeneous effects, whereby, not surprisingly, electricity-intensive plants are more heavily affected, and those that don't have access to self-generation. Beyond that, economies of scale and self-generation really does affect the smaller and medium-sized plants as opposed to the larger ones that have the ability to cope with shortages. So I'll go through the model that we use, the theoretical model, kind of quickly and just focus on the takeaways from that. There are a lot more details in the paper. But we start with the daily production function, which has your standard 3 inputs, but we classify them in a way that sort of is useful for thinking about this. And these are capital, which is fixed within the year, labor, which is semi-flexible, meaning that it can't be changed day to day, but it can be changed within the year, and materials, which are storable. Okay? And electricity is used in fixed proportion to production. So on any given day, you say an outage occurs with a certain probability. I'll show what these observed probabilities are in a minute. And there are different effects for different types of firms. So we have a revenue generating production function, and we take first order conditions, all that kind of profit maximizing stuff. The takeaways from the model are that there are very different effects for those that can generate themselves and those that cannot. Non-generators experience 2 of these effects, the shutdown tax effect, which is that prospectively, firms will reduce labor inputs because it's going to be wasted during shortages. They will hire fewer workers because of unpredictable shortages causing them to lose the cost they incurred for their labor. There's also the obvious shutdown effect, which is they cannot produce during outages. Because of the way that we model this, that electricity is used in fixed proportion, firms just can't produce when there's no electricity available. Okay? Output is exactly that percentage of shortage time, and TFP, or productivity losses, are moderated a bit. For those that can cope through self-generation, there's an output tax effect, which is the larger of the 2, which is really that self-generation just is an incremental per unit output increase in costs. Okay, so it acts very similarly to an output tax. Okay, it also causes them to reduce inputs because of this increased factor cost. There's also a small input variation effect, which comes from the model and essentially comes from the fact that a constant flow of inputs results in higher production than a variable flow. But really, the output tax effect is the larger one here. Okay? So for the study of textile manufacturers, I'll show a histogram of production. They're actually, well, these are density plots, for one given plant that sort of helps me make my point. And each line on here is a day of the week. The blue lines are the days of the week where the plant did not experience power outages. The red line is whichever day of the week this particular plant was experiencing power outages. So you can see that on, say it's Sunday, that they experience the power holiday. This is the planned one, remember. And you can see that most production on those days, Monday through Saturday, are in a similar range. On Sundays, there are some days in which they definitively cut output to about half of what it looks like, about half. So perhaps reducing by a shift or two. And then some days they actually are able to produce the same amount that is produced on non-power holidays, presumably through self-generation. Okay. And these textile plants are quite large, in fact. They all have the capacity. This is just the sample that was used by the co-authors of the other paper. They all have the capacity to self-generate, and they're running basically 7 days a week and 24 hours a day, aside from any time that they're down. So this is just an example of the data in one of the plants that makes a good point to show what's going on. When we assess the effects of the power holidays on output, this is a set of regressions on the daily production, looking at how much production is reduced on a given power holiday. So let me see if I can point here. I'll look at columns 1 and 2, which give precisely the percentage reduction on average across the set of plants that is accommodated on those power holidays, which is between 7 to 9%. Okay? This is not a small number. We definitely think that this is sizable, and this is as was stated, these are short-term effects. Okay? When we look at the sample, when we actually include or do an interaction with the degree of unplanned shortages in the area over the time period, we find that the effects on output are actually worse when there are both planned and unplanned shortages. Okay? That's output. When we look at costs, we look at how much energy costs increase when production is shifted from non-power holidays to power holidays. Okay? And this is going to be detailed a lot more in the paper, how these were constructed and et cetera. But the average in columns 2 and 3 increase in costs, and this can be interpreted as shifting 1 unit of output from a non-power holiday to a power holiday, where firms are, in this case, generating, is an increase of 79 to 82%. So in terms of the energy cost that goes into that unit of output. So it's not quite a doubling of the amount of energy, amount of cost going into producing that unit of output, but it's quite close. And this is actually quite close to the magnitude that we've heard anecdotally and from other sources. Okay? Or another way to put it is that shifting 100% of production, which, I mean, is just a thought experiment, from non-power holidays to these power holidays would increase monthly energy costs between 60 and 80%. Okay? So when you actually calculate this out and you want to get the input cost effect, you can take the amount of output that's produced on power holidays on that given day of the week, which is approximately 11% across our sample, multiply it by the increase in energy costs when the firm is self-generating, 80%, times the share of costs that are comprised of energy, 2%. This input cost effect for these plants at least is quite small. It's less than 1% for them to deal with these once per week power holidays. Okay? Compare that to the output loss that the plants are facing, where 1 out of 7 days they're facing a power holiday. On that power holiday, they lose 7% of output. So they lose about, due to these shortages, about 1% of their output, which really is not a whole lot. On the actual day itself, it's 7 to 8%, but given that it's only 1 day in the week, not so much. The effect on TFP is even smaller because for these textile manufacturers, capital, which is the fixed input, goes unused during the outage times. Capital only comprises a small share of the inputs, about 5%. And so the fact that 5% of your factors of production goes unused is not a huge deal. So going to the nationwide analysis where we use the shortage data, these are gathered from the Central Electricity Authority, and they have measures, of course, which is captured quite clearly in terms of supply. And then they come up with a calculation for demand, which is the quantity that would be demanded at the current prices. So this comes from some analysis by the CEA itself and also the regional power committees. So we have a measure of shortages, which is the shortfall from assessed demand. And I won't go through the whole table of summary statistics. I'll just point you to the third line here, which sort of gives a sense, which is the shortage measure itself that I just described. And this says that across states and years, this goes back 1992 through 2010, the average state year shortage or shortfall from their assessed demand was about 7%. Okay? That number masks a good bit of variability within states in shortages over this period. I'll point to 2 examples. So the green dotted line, Karnataka, had very high shortages in the 90s and almost into the 2000s, not quite. And it came down towards the end of the period, and it's starting to spike back up. Maharashtra, which is the solid purple line, was quite low in the 90s and has been growing, and it also is one of the states you hear a lot about in the media as having suffered a lot of losses in the last couple of years, and you can see that it's growing. And this is the variation that we're going to use, part of it, to identify the effects of shortages on firm output and productivity, et cetera. So looking at the annual survey of industries data, again, I won't go through the whole thing, but I'll point out a few relevant aspects. So the third line down, total persons engaged, the average plant in our data has about 164 people employed. These are quite large plants generally. The annual survey of industries covers the organized sector, so it does not cover home-based production and other informal sector plants. Okay? Approximately 54%, this is in the middle of the, where is it? One, self-generator. 54% of firms are observed generating their own electricity. So there are some firms in here that have the capacity to cope and deal with these outages and some that do not. Okay, and the average plant, down at the bottom, the average plant is observed 6 times in the panel. So to get a sense of some of the data and the degree of self-generation in India, we plot here industries and their relative amount of electricity consumption that is self-generated in the US versus the relative amount of electricity that is consumed that is self-generated in India. So for example, pulp and paper, which is the one that's closest to me here, 80% of the pulp and paper plants in the US, 80% of energy consumed in pulp and paper plants in the US is self-produced, whereas in India, it's 60%, approximately. But what we see over in this area here is that there are many industries that are producing their own electricity that in India that are not really producing very much in the US. So this sort of just shows the degree of importance and how much more frequent is self-generation in India compared to the US.
Why?
Great. So another quick stylized fact is that self-generation varies greatly with plant size. So here we have the log number of employees. So at 10 employees, approximately 20% of plants generate their own electricity. At 1,000 employees, at Mark III, about 80% of those plants are generating their own electricity. Okay, this has important implications that I'll talk about as I get to the end. So our estimating equation is really any set of outcomes. We're going to look at output and productivity mainly, and those are what I'll talk about in a second, and the degree of shortages in predicting those. Okay, we'll use a first difference equation, but we also do fixed effects, et cetera, et cetera. So to get over the endogeneity problem, we are going to use hydroelectric generation as an instrument for shortages to identify the effects of these shortages on output and productivity. And the claim is that hydroelectric generation ultimately comes from weather, which is really, and other things, of course, but really not related to the outcomes of interest here. And there's a great deal of difference in hydroelectric generation within states over time. And we actually, it is the case that the hydroelectric generation does predict or does have some power in predicting shortages. And I'm showing this from one example state, Karnataka, where the hydro measure is marked in the red line here, and it more or less inversely moves with the measure of shortages over time quite well. Okay? So in terms of results, I'll go through just the main two that I've been talking about here in columns 3 and 4, revenue and productivity. And these point estimates show us that if you increase the level of shortages from 0 to 10%, you have a loss of revenue of about 6%. Okay, these are very similar to the textile estimates, and also at the same time, the loss in productivity is quite small. And in this case, there is no loss, but it's imprecisely estimated. Thanks. When we look at heterogeneous effects by different types of firms in electricity-intensive industries suffer much greater revenue losses, and those with a self-generation capacity are able to moderate those losses to a good degree. Still, all the same, no effects on productivity, or if there are effects, they're quite small and difficult to identify. So I'll talk very quickly about what this graph implies. And if you take as given this stylized fact that self-generation capacity is really not accessible to many plants, those in the smaller end of the spectrum, and you simulate the effects of shortages for plants of different sizes, it ends up being that the smallest plants, not really surprising, suffer the greatest losses. Now, our estimates are about 5 or 10% on average across the sample that we used. Now, in India, in both manufacturing as well as service industries, the mass of labor is concentrated in this area, those firms that are experiencing the highest losses. So that's just, I think I have a minute left, so I'll just conclude. So businesses in India and elsewhere are reporting blackouts as the most important proximate barrier to growth, and we do find that in the short run, these shortages do result in large revenue losses, but the productivity losses are small. And the heterogeneous effects, because of economies of scale and self-generation, this implies that small plants are more heavily affected and can lead to an additional distortion in the firm size distribution. There's some discussion in the paper about the use of interruptible contracts where providers can segment the market into those plants which could choose to receive shortages, presumably those plants that could generate themselves, whereas those who need non-interruptible contracts would select a different arrangement. So that's in the paper, not too much time to get into it now. Thanks.
Thank you. Thank you, Stephen. We're now a third paper that tries to assess the benefits of expanding energy access. This is indeed the title that is in the program. The title here is slightly different, but the focus is again on this kind of assessment, and the presentation is going to be delivered by Hussein Samad from the World Bank. I'm very pleased to have you here. Thank you, and the floor is yours.
Thank you very much for inviting me to present this and share the findings of a recent study that was conducted by the World Bank. And the findings of this study is going to appear soon as a World Bank book. And in this study, we basically looked at the solar home system in Bangladesh. And in my presentation, I would like to discuss 3 aspects of the study that we looked at. First one is the market, solar home system market in Bangladesh, and I tried to explain a little bit why it is very successful. In fact, it is the fastest growing solar home system in the world right now. And the second is about our study, how do we analyze the benefits of solar home system access and the data. And third, I tried to cover very little bit about how these benefits and the demand that can be sustainable over a long time. So first, this is the context of Bangladesh. In Bangladesh, 75% of the people, they live in rural areas, and grid electrification rate in rural areas is 35%, and whereas in urban areas it is 90%, and overall it's 50%. And Bangladesh government has a vision of providing electricity to all citizens by 2020. And the problem is in rural areas, the electrification is provided by an organization called Rural Electrification Board, or REB, which was very successful in expanding the electricity in the 90s and early 2000s. Basically, it didn't do well at the later half of the 2000, the decade of 2000. It's because actually there was a nationwide generation crisis, and that institution, REB, they do not actually produce electricity. They get it from the national source, actually, and that was affected by the generation problems. So the grid electrification scheme actually went on very slow at the end, the second half of the 2000 decade. And also there are areas in Bangladesh which are very remote and covered by river and islands, and that areas are not very suitable for grid electrification expansion because, you know, they are not monetarily profitable for the implementers. So the government actually thought seriously about expanding electricity using alternative sources, in particular renewable sources. And they also got advices from international donors, for example, World Bank, and who actually persuaded the government to go for renewable energy, solar home system, and others. So based on that, the government actually, in the most recent 5-year plan, they have allocated that 5% of the electricity has to come from renewable sources. And the agency which is responsible for implementing renewable energy in Bangladesh is called ITCOL, Infrastructure Development Company Limited. Even though they started actually in the late 1900s, 1997, as an organization to do financing for infrastructure, mostly, and then they went on to renewable energy. And when ITCOL actually started this program, in 2003, they got support from all these different international organizations, donor organizations. And the program actually started with a very modest target, 50,000 installations over the next 5 years. But I'll show you in next slides how the solar home system actually expanded throughout the Bangladesh. It actually exploded, in fact. Now, for last few years, they are installing 50,000 systems per month, when initially the target was to install 50,000 installations over 5 years. And by early 2014, total installation reached 3 million. So this is the year-wise installation. If you could look at, in 2003, the installation was 11,000, roughly about 12,000 systems. And then you see how it went up. And in 2013, they installed over 850,000 systems. And this is the cumulative growth of solar home system installation in Bangladesh. And as it's, by the end of 2013, it is 2.7 million. 2.7 million, and roughly about 10% of the off-grid population of Bangladesh. And this is just to review about the solar home system technology. There are three main components. One is the solar panel, which is installed in the roof, and then there are, it actually converts the energy from sun to electricity. And then there is a battery. If you look at the battery, that is actually stores the electricity so that households can get power during nighttime or in a day when it's cloudy. And there is another component which is called a charge controller, which actually controls the flow of electricity to the battery so that it doesn't get burned. And these solar home system unit, they come in different units, 100, 80, 85, 50. And I gave an example of a 50 watt power capacity, which actually can power 4 lights, a mobile phone charger, and a television set. But over time, because of the technological advancement, first, the price of the solar home system went down, and second is what was the capacity of a 50 watt peak system could do now is possible with a lower capacity system, maybe 20 watt peak or so. And this is the administrative structure of the called solar home system program. It is important to understand this structure because it is because of this structure the program is so successful. And this program, I mean solar home system program, has been tried in many other countries around the world, but it has not been as successful as it is in Bangladesh. And this will probably explain why. The administrative structure, if you look at, there are different actually bodies, and ITCOL actually get the money from the donors, and which it provides to the POs. POs means partner organization. These are the implementing agencies who actually go to the household in a rural areas. They convince the household that you should buy this solar home system, and you will benefit in the long run. So the POs, they get the money from ITCOL. And ITCOL gets the equipments from a supplier, and supplier has to meet certain technical standards so that the product they are giving, they are reliable and good quality. And there is a committee to verify that, technical standards committee. And once ITCOL install, the POs install the system for each household, they actually ask for reimbursement for the money from ITCOL. And ITCOL actually checks the installation, how it went on, and checks the quality, and then they give the money back to the POs. And POs, they have to apply. There are new POs coming in every month, so they have to go through a selection process, and there is a selection committee who actually decides if this PO is qualified to do the program. And there is another operations committee which actually tries to solve different kind of implementation problem. So this is the pricing mechanism. This is also very important because how the price is borne by the household, it actually determines if the program will be viable or not. So I have given an example of a 50 watt peak system, and the market price of this, I mean, during the data I use, it probably has gone down by now. Say it is $400 US. And to install these, the PO, the implementing agency, they get a subsidy of $25 from ITCOL. And that subsidy actually started at a higher level in 2003. It was in roughly about $70, $75, and it gone down to $25 nowadays, and eventually this subsidy will be eliminated. The purpose of the subsidy is to allow these implementing agencies like POs to penetrate the market, so that at the end of the day, even when the subsidy is taken off, the market will be there, and there will be a viable market because there is a profit to make. So for $400 system, the POs get a $25 subsidy. That makes the price to households $375, and household pay a 10% down payment, which is $37.5, and that is the that leaves $337.50 to be paid by the household. And what happens is, if you look at the right side, that amount is given as a loan to the household, and household is supposed to pay that amount over 3 years. Sometimes it's 5 years, but I gave an example of 3 years for a flat interest rate of 12%. That makes the total payment of the household $450. That means monthly payment is $12.75. So the idea is the price of the original system to household, which was $375, that is not affordable to the household. So this is how the system is made affordable to the household through a microcredit scheme. So that, I mean, they pay a monthly the interest rate and a lower monthly payment, which is $12.75, which is very much affordable for a household like that. And that's how the system is actually selling so well in Bangladesh. And for the PO, when PO actually extend the loan of $337, they get 80% of that money as a loan immediately after installation from PO, and they get the loan at 6% interest rate for 6 years. So look at the difference here. The POs, they are giving the money to the household at 12% rate for 3 years, but 80% of the money they are getting from EatCall at 6% rate and 6 years. So they can actually recycle the money twice during the loan period. And that's why they are making money in 2 ways. One is they are getting money at a lower rate, and also there is a longer period of payment. And EatCall gets the money from the donors at a 3% interest rate over 15 to 20 years. So everybody, it is a actually win-win situation for everybody. And these are just a profile of the POs. And the most dominant PO is Gramin Shakti. You probably heard of Gramin Bank, the microcredit organization, which is very renowned in the world. They have a subsidiary which is called Gramin Shakti. They do actually install this solar home system in Bangladesh. They have the highest share of the market. And what these POs do, they not only just install the system in the household, they also train household members, preferably women, in different types of, technical solutions. Like the women, they become technicians. They train the women to become technicians for this system, so that in a village, if there is a problem, instead of some of the PO technician going to the household to repair the system, there is a women who have been trained among the users as the technician. They do the fix up, and they also make money out of this. And they also learn, who are good, how to install the system also. This is a picture from the Gramin Shakti's training. If you look at the left figure, it shows that the training is going on how to, do repair works of different parts of the system. And on the right side, you can see a woman who actually went on the roof to install a system, which is quite unusual for a developing country in Bangladesh, but that is how these programs operate. Now we look at how we actually conducted the study. I'll describe a little bit about our data. And so basically what we did, we have actually 4,000 households, and these are the major regions of Bangladesh, and this actually describes how the sample was selected. There were 1,600 solar home system household altogether in the sample, and 2,400 non-users. And this is the distribution of solar home system adoption from our data, and it is actually nationally representative. It shows that 8% of the off-grid population or households were served by the solar home system in Bangladesh at the beginning of 2012. Now it has become 10% of the off-grid population. And this is actually the same figure, but I've tried to give it by the adoption of, by the capacity of the systems that were adopted by the households. And we can see that 50 watt peak is the most popular. Actually, it actually sold the best. There is a reason for that, because with a 50 watt peak system, you can actually use 4 lights, a black and white TV, and also a phone charger. And now I'm actually discussing about the benefits of the solar home system. One of the way to calculate the benefits is the gains in consumers, what they call consumer surplus. Consumer surplus is actually, mathematically, it is the difference between, for any product or services that a household wants to adopt or procure, if what is the amount the household is paying, actually paying, that is called, let's call it AP, and what is the amount the household is willing to pay. Usually willing to pay, this amount is larger than the amount they actually pay, and the difference is consumer surplus. And when, so for a household, if you look at the graph, QK is the price of kerosene, and PK is the amount of kerosene the household consume. And when they switch to electricity, electricity price is definitely lower. When you think about in terms of the lighting unit, which is kilolumen hour, so because this price is lower, household consumes a lot of that in terms of electricity, which is QE. So basically, the area under the demand curve, that is actually gives the amount household wants to pay. The actual amount the household pays for kerosene is B plus D. For kerosene, it is B plus D. That is, we just multiplied the price and quantity. B plus D, that is the actual amount the household pay, and the willingness to pay is the area under the curve, which is A plus B plus D for kerosene, willingness to pay. And actual amount is B plus D, so the consumer surplus is the area A for kerosene. And for electricity, the amount household pay is D plus E. And the actual amount the household is willing to pay is A, B, C, D, E, area under the demand curve. So the consumer surplus for electricity is A plus B plus C. So if we subtract the consumer surplus of kerosene from the consumer surplus of electricity, you will get actually B plus C. So that is the gain of consumer surplus from switching from kerosene to electricity. I could have actually included this in the slide, but I thought I'll just cover it without it. It will make it more time consuming. So that is one way to calculate the benefits. So this is what we got from our study. The price of the kerosene lighting that non-SHS households pay is 51.3. That is Taka, the local currency of Bangladesh, per kilolumen hour. And the quantity they consume in kilolumen hour is 7.7. On the other hand, the price of electricity from solar home system is 1.4 Taka per kilolumen hour. You can actually see the difference in price in two products. And the quantity they are consuming is 26.3. So gain in consumer surplus is 607 Taka per month, which is roughly about 5.5% of their monthly income. So there is a consumer surplus. You have to understand one thing, that this is a benefit which actually the household does not gain, or it does not accumulate that amount. It is a potential savings. It gives you the potential savings. It is not the actual accumulated savings. So that is 5.5%, and this is a common way to calculate, electricity benefits or other benefits when the household switch from one product to another. And there is another calculation that we did actually, how much CO2 emission was avoided by the solar home systems in Bangladesh. If you look at non-household, non-solar home system adopters, they actually emit 6.9 kg of carbon dioxide per month. Compared to that, the solar home system households, they emit 1.4 kg per month. So the difference is the savings per month for a household in carbon dioxide. So if we translate that, 5.5 kg reduction in carbon dioxide per month translates to 160 million kg in carbon dioxide emission avoided every year for all solar home systems in Bangladesh. I have just multiplied whatever the number of consumers of solar home system. And considering that only 10% of the households in the off-grid areas have adopted solar home system, the potential savings could be really, really high. Then, now we tried to assess some benefits using impact evaluation, econometric techniques. The outcomes we looked at: children's education, income, expenditure, and asset, health, and women's time use. So, this a collection of solar home system of the solar homes is not random. Experimental design could not be done. That is called the, but that cannot be done. We try to use experimental non-RCTs, and one of my earlier stated the table method do the impact evaluation, but we could not find good for the adoption because it has to fulfill. One is it would be able to influence the adoption or persuade the household solar home system, but influence the outcome, income or study behavior. Particular scheme we could not find. So what we did, implement an alternate which is called propensity, also common in impact evaluation. Basically, just give you a simplified which I think important for them, those characteristics between the solar home households. It is actually done index which is called propensity score, which is underlying characteristics and influence a household for are households, adopters, and those households that in these characteristics, then the outcomes used to households, and we call the impacts. This is the first set of findings, and we find that as 5 to 8 choose for the stars and girls, enrollment rate and schooling years as a result of. Then we also per capita income, and we found that the home households 12.3%, expenditure which is 5%, and also we looked at the goods actually, and we saw that they have a 26 goods than the non-adopters. And here comes, and once the household actually the first use it for lighting and the lighting. So when they replace, as you already know, the presentation, the lighting, they are actually major causes of insoles and indoor pollution, adverse of these, the rest and all those things. From our study we did not find, definitely, but we did not find that is statistically significant. PSM matching, even at the descriptive data, we did not find it. We actually tried to find benefits that actually come from this, and the practices that is through knowledge and information. Maybe those households, system owners who have kind of things, they have a better that might translate better hygienic behavior, and as a result, maybe some impacts. That is exactly what we found. That the respiratory actually 1.7, then also that also went down. Found for this reason we focus on young children who are most exposed in a non-goals. 1 minute. Okay, so there are women's time use, fuel wood collection that are down. Also, women's entertainment for education, any other reason that went up. Tutoring in children's education solar home system. Market potential. The issue is program is sustainable. That the price of the solar homes is one of the most determining factors. Adoption of solar home system, the price, and by unit price. And we found we actually function, and from that we actually do a simulation what is the release to the that, it clearly shows that of the adoption as the price. We looked at 3 major subsidies that the innovation agencies get, there to it actually, and we found that the elimination, but there are 2 other gates. PO gets it call, the 6% interest, and get a subsidy. The donors get a 2 breaks, one is cycle and the interest subsidy have to be maintained sustainable over long, and that's about it. So I'm done. Thank you.
It's a quite impressive kind of program. Should get the support not just from microcredit institutions, one's BRAC and the other ones, also from international organizations, the World Bank, that should probably kind of just study, that even support, which is good to know. I mean, because in things. Questions? Are there? You have a question?
Good morning, Emanuela Colò, Milano. I apologize, I'm an engineer, so sorry to all of you. First of all, your presentation. I have all of you, but I will face-to-face discussion that can be of interest for all. We have discussed the issue. We have space electrification from the small home PV. But we have the microgrid system with solution, and which is indicated by the International Way for Achieving Universal. Listen, your opinion on related to microenergy and also hybrid system.
Thank you. Is there anyone? You can.
In Bangladesh, what ITCOL is doing, which is implement system, they are also future microgrid system. They did not do it, it was not affordable, and also actually supports not just only did a number of farms who need it. They have actually come out a scheme to implement solar home based Bangladesh, which will support households or in a market, a community. They are doing it and financed it, and hopefully impact evaluation on that too.
Please.
I think these grids are very appropriate for a lot of islands, a centralized system. One question is, obviously, their sort of benefit might be when you have disasters and hurricanes, grids will not all break. So out from this session is that the access are so even think of these systems.
Caroline?
Thanks for a great. So I initially had this giant, but science on it, and so so you're doing high impacts on energy quality, and so I was wondering, since you can put that in the context of actions that we might make in terms of is this to interventions in education or other we might have, and then Steven, since you are kind of output tax having to generate your own the extra cost of that, can you sort of then back out one of mitigation electricity costs?
Thank you. Thanks, Rushan.
Yeah, Jen, so okay, let's not transmission lines to worry about improved reliability. That, of course, recovery, institutional of theft, and their example that basically. So yeah, those are really one could make.
I don't have and I apologize. It's definitely like to go, but as far as done so far, it's I think, but.
Donny from FEEM. And I have a question for Steven. Trends that are very large, but maybe not so large level from the study that you showed about these huge results, not large, just ones do it. And there are a lot of. Can you do any other measures, such as on labor, women, and stuff like that?
Briefly, that the estimated that are small, but take into account that the smaller firms, medium-sized firms are experiencing. This also presents bad firms. And it doesn't particularly, in our case, affect wage and affected. It certainly affects over a time. Yeah.
Other questions, remarks, curiosity? No. You may have found this announcement, some of them. This is the announcement practice contest. So that the Expo is launched was on management, and in particular increasing energy. This one is on, and this is why we're in this new conference, and climate practices these ideas and already implemented of new reduce energy. There is a website of this best process, a new contents, and the new video just to what we plan to do and what. Alessandro. Thank you. Ideas can be submitted to Shonali and myself are among those who will these different practices. Of course, we are funding idea, propose funding institution to support them. So please, in the meanwhile, enjoy later 2:30.